introduction. My name is Tom Tainer. I'm the Technology Executive for TMEIC Corporation. TMEIC stands for Toshiba Mitsubishi Electrical Industrial Corporation. It's a global company with offices in main headquarters in Tokyo, Japan, several offices in Japan, office here in Roanoke. The North American headquarters is here in Roanoke. We have offices in Houston, also in Beijing and Shanghai, China, Singapore, London, Italy, Sao Paulo, Brazil. So we are a truly global corporation. My profession, I'm an electrical engineer. I'm an E in STEM. It seems like there were a lot of biology teachers in the classroom today based on the questions that we heard earlier, all very well informed and very interesting. So hopefully I can provide as much interest as John did in his speech. But the company I work for specializes in industrial power conversion, drives and controls, and industrial process automation. Now, I know that doesn't sound exciting, and most times when people ask me what I do for a living, and I tell them, they immediately want to change the subject to who won the Super Bowl. So to give you a little bit of an idea, I am going to show you a video, an instructional video, not an instructional video, but basically an advertising video from our company. It gives you, it's about 5 minutes, and it gives you a little bit of an idea of what we do, and ignore all the how wonderful TMEIC is. Really pay attention to the industries and products we serve, and it gives you a good idea of what we're about and the kind of engineering and science disciplines that are involved in working with our company.
TMEIC is a global leading industrial system integrator, providing cutting-edge technologies, products, and automation systems for a wide range of industrial applications, including metals, crane automation, the oil and gas industry, mining, large-scale utility solar power, utilities, cement, and more. TMEIC was formed through a powerful alignment of global leaders: Toshiba, Mitsubishi Electric, and GE. These three companies have long been leaders in the design and application of high-quality, high-performance power electronics and electric motors. Building on this experience, TMEIC has earned a reputation for delivering value to our clients with reliable, state-of-the-art industrial products and system solutions. Advanced technology, excellence in engineering, and years of accumulated experience are at the heart of TMEIC's success as a world-class system supplier. In metals, TMEIC uses capabilities built on 60 years of steel mill experience, supplying comprehensive high-performance control solutions for steel and aluminum rolling mills, and is the leading global supplier of hot strip mill automation. Our reputation is indicative of our full range of automation capabilities, with the ability to supply complete systems, including motors, drives, programmable controllers, networks, HMIs, process modeling, and process control software, as well as the support of legacy systems. Working in close cooperation with our clients, our experienced team delivers innovative, world-class solutions to technically challenging applications. TMEIC has over 50 years of crane automation experience. With over 2,200 installations worldwide, TMEIC pioneered the automation of stacking cranes in shipping container terminals, such as this facility, which has 30 unmanned gantry cranes, all computer-controlled. Our control systems are designed to meet the most demanding applications, and our extensive experience provides customers with maximum crane productivity. Every step of the way, from the wellhead to the finished fuel products, TMEIC is playing an essential role for the oil and gas industry. In offshore platforms, liquefied natural gas plants, as well as oil and gas pipelines, TMEIC provides reliable, high-power, high-speed motors and drives, resulting in energy savings and high efficiency. In the mining industry, TMEIC has served hundreds of applications in processing ore, minerals, rocks, and coal worldwide. Maximum uptime and long-term reliability are critical to all applications in surface and underground mining, including ball and sag mills, conveyors, crushers, separators, feeders, weigh stations, pumps, mine hoists, and many more. Solar-powered electricity generation offers a powerful renewable alternative to secure our energy supplies. TMEIC is a pioneer in power electronics for photovoltaic inverter systems with more than 25 years of research and experience invested. Our SolarWare PV stations provide cost-effective solutions for large-scale utility PV plants. TMEIC SolarWare inverter products include advanced grid integration features designed to meet the most stringent industry standards. Our main site controller ties these products together to provide maximum power to the grid. Features include advanced dynamic power factor control, voltage control, plant power curtailment, plant ramp rate control, and sequential start and shutdown operation.
Okay, hopefully that gave you a little bit of an idea of what we do. So the term industrial automation, process automation, at least you have a bit of a frame of reference. But really, I will add some elements of what we do and how we do it, why we do it as part of my presentation. But I took a little bit of a different approach when I thought about what to present and how to present. The idea of, as John noted in his speech, we need good, talented, committed people in all areas in all the STEM professions. Certainly engineering is one of those. We're having trouble recruiting good engineers in this country. The United States is graduating engineers not only on a total rate, but a per capita rate much lower than Europe, China, and Japan, which puts us at a tremendous disadvantage if we want to maintain our technology edge. So the question becomes, why is it so hard? Why is motivating young people to pursue STEM professions, why is it such a challenge? Well, I had a couple little anecdotes I think kind of give some insight into the problem. The first is a story of an article that was in the op-ed of the Roanoke Times about maybe 10 years ago. It was written by a Virginia Tech business major during National Engineers Week. Now, in case you're curious, 2017 National Engineers Week starts Sunday. If you're looking to buy a card for the engineer in your life, I don't think Hallmark makes them, so you might have to do a little research on it. Long story short, the tone of this article from this business major at Virginia Tech was he had a brilliant strategy for how he and his business colleagues, business student colleagues were going to get rich. They were going to start a company that hired engineers, sold them for what they thought they were worth, and then only pay them what they were actually worth. The idea being that engineers think very highly of themselves, but in reality, their value to society is not so significant. Just a bunch of nerdy people sitting in the lab playing with their computers and their fancy electronic toys. Of course, this was written by an individual, I'm sure, got up and cooked his breakfast in a microwave, drove his car to school, stopped at Starbucks on the way, bought his $8 cappuccino by swiping his debit card and automatically transferred funds from his bank account to the company, wrote up his letter on a personal computer using probably Word, sent it in over the internet, and all these wonderful things that he took for granted on a day-to-day basis and did not appreciate how good they made his life. He dismissed as unimportant and trivial, and the minds and the intelligence and the creativity behind that was not worth a second thought. A man at that age should have known better. Why did he not appreciate the marvels that, STEM professionals brought to his world? That's one problem. Now, the other anecdote is the story of my one granddaughter when she was 1.5, probably about 1.5 years old. Not old enough to talk, but a few words, but old enough she could kind of walk a little bit, toddle across the floor. One afternoon, she was sitting on her mom's lap with her grandma next to her, and Mom and Grandpa were viewing family photos on Grandma's iPad. And then she'd swipe back and forth to change the pictures, and and every time she did the swipe, the picture would change, and my granddaughter was sitting on her mom's lap taking this all in. When they were all done, Grandma and Mom sat her on the couch. They went into the kitchen. Well, her daddy was watching something on TV, football or whatever it was, but she decided she didn't like what was on TV. So she toddled up to the TV as best she could, swiped her hand across the TV, kind of stepped back expecting the picture to change. Didn't change, so she swiped harder. Still didn't change, so she went and she swiped the other way. Still didn't change, and she kind of stepped back, and in her little mind, it's another little data point in her learning little mind that thing works that way, but that thing doesn't. But the fact that she had absorbed, it's just a fact of life, that by swiping your hand across this thing, the picture will magically change. So for her to take, as she got older, and she's only 4 now, but as she got older, technology being a part of their life, they take that stuff for granted, but I can understand that. Because in their little worlds, it was always there. It's just a part of how the world works. But it's really symptomatic of the same problem. We take things too much for granted. The marvels that STEM professionals make available to the world are dismissed, underappreciated, taken for granted, but they define our age. The modern age is defined by the devices and the tools and all the wonderful things that STEM professionals bring to our world. So, what's the challenge you face as educators? Well, how do you awaken young people to the excitement, importance, value, and opportunities that occur in science, technology, engineering, or math? How do you help them understand that they are capable of a STEM career? That it's not that hard. It's not easy, but it's not prohibitively hard if you're interested and want to pursue it. And then when you find that mix, that magic mix of interest and aptitude that are critical to success, how do you nurture that? How do you provide them appropriate guidance so they can make informed decisions about what to do with a career? And if they're interested in moving in that direction, how do you help them make the proper steps in that direction? The way I would approach the problem, you have to in some way open their minds to the fantastic disguised in the seemingly simplistic and intuitively obvious. The simple function of swiping across an iPad is so intuitively obvious, that it is so user-friendly that people don't appreciate everything that goes on behind the scenes in terms of computer software, computer hardware, sensors to detect a finger moving across the panel of that iPad. To understand the intensely complicated, incredibly creative stuff going on that they don't see. So how would I do it? I would challenge them with what makes it work questions, and challenge them so often that it becomes part of their thinking. Whenever they interact with one of these devices in their life, take a moment to think, well, how does it do that? How does that credit card transaction get from here? I swipe my card, it goes from this machine over the internet to the bank. It transfers funds electronically to the vendor. How does that happen? You've got hardware involved, networking software. You've got accounting software. You've got all these wonderful things going on in the background that just happen in a blink of an eye. So, some examples of questions you might ask them. Here's a typical smartphone. This is a very small subset of the features and apps that are available on that smartphone. Ask them a few simple questions. Okay, what's behind that maps function? You get on the maps function and you figure, I want to go here with a little bit of swiping and pointing and clicking. I say, I want to go here to here. And it comes up and there's a map and it talks to you and it tells you when to turn and it tells you how far you got to go and it tells you when you're there and it tells you where the restaurants are. What's behind it? Well, you've got, again, sensor technology and software in your iPhone. You've got networking technology that sends it wireless communication to a station, routes it. You know, you're linked up. The phone's linked up to a GPS system. It's taking GPS signals, doing some calculation, mapping that with data about location and maps and all the things associated with that map. Not only position, but all the amenities that go with every city, town, and village on the route. And when it tells you that you're going to get off at the exit in 1/4 mile, if you stopped your car and measured it, it would be 1/4 mile. Not an eighth of a mile, not 2 miles, so it's spot on. Ask them just to consider how that's even possible. Some other questions you might ask them, and these are all opportunistic and contextual. You kind of ask them. You don't need to know the answer. You don't necessarily want to know the answer. You want them to be so intrigued that they are motivated to go find the answer. Magnetic resonance imaging machine, a computer-aided tomography machine. As John talked about in his speech, the tools available. Everybody appreciates the physician that can diagnose cancer and prescribe a course of treatment. Do they appreciate the scientists and engineers that created an MRI machine or CAT scan machine? Before those machines existed, the only way you could go in there and find out if there was a cancerous tumor was probably invasive surgery. You had to go in and had to do a biopsy. Now, you get pictures with such incredible resolution that they can diagnose a tumor down to maybe a millimeter or less and determine a probability that if it's malignant or benign. So everybody, again, appreciates the physician. Do they appreciate the tools that were given to that physician to make his job, to amplify his intelligence, give him tools to do diagnosis that allow him to come to a conclusion quicker, with far more accuracy, with far less invasive procedures? Simple things like how does a microwave oven work? A full-length animated movie. Somebody sits down and watches something from Pixar, and they're entertained. They laugh. They get engaged in the movie. But do they ever think about the computer software technology that made that movie possible? Just the other day, I was watching Trolls with my granddaughter, and watching that movie a few times, I focused on a couple things. Very entertaining movie, by the way. Highly recommend it. But there were a couple of little things that caught my attention. At one point, the Princess Troll was holding a torch, and I was watching the flame flicker on the end of that torch. And I'm thinking, suddenly my mind was focused on how much software was behind the simple thing of making that flame appear to flicker on the end of that torch, and how really complicated. It's such a simple thing, just a little bit of a movie, of one scene, one little square-inch segment on the screen. And there's tremendous complexity behind that. And to give the movie makers, the filmmakers, the creative tools that amplifies their creativity. It takes their creativity in storytelling and animation and gives them, it brings it to a level that even a few years ago was probably inconceivable. The self-driving vehicle, everybody's talking about that now, but ask one of your students to say, okay, how are they going to do that? Ask them to walk themselves in their mind as simple an act as, I'm going to change lanes on the highway. Well, let's even go before that. Okay, you're on the highway. The car's got to decide the speed limit's 65. Do I go 65? Or do I go with the flow of traffic? Is 65 the speed limit? If everybody's going slower because of bad weather, does that create a hazard? If it's good weather and everybody's going 75, does going the speed limit create a hazard? So simple decisions that are simple for a human being, to embed that intelligence in a machine is incredibly complicated. The applied mathematics and algorithms and software and everything and the sensor technology to make that happen, and now you want to change lanes. Well, if you're a driver, you put on your turn signal so everybody else around you can understand your intentions, and you kind of wait and make sure everybody's kind of with you. Nobody's moving into that same spot. You change lanes. A simple decision, simple action. Put that intelligence into a computer. What kind of sensor and communication technology is necessary for that? The car you're in, the autonomous car you're in, to tell every other car around you, I'm about to move. I'm about to change lanes. Make sure they all got the message and they understand, and they're not going to be moving into the same space. And what if one of those cars is not autonomous and it's driven by a human, and he's not talking to the car with the computer, so he's going to move into that spot? How do you deal with that? So we think of autonomous cars as, oh, it'll just a matter of time and it'll happen, until you start to think about what's involved. And these are not even things you want the student to research they can answer. They can't. You want them to be intrigued by the wonders behind the scenes. Sorry, some other thing, World of Warcraft, a game they play every day. What does it take to have a fully interactive, game like World of Warcraft? Simple as the audio system in your car, virtual reality. The idea of virtual reality, what does it mean? And how do you do it? And what are the implications? Something Siri, how did she get so smart, and how does she work? You pick up your phone, you talk to Siri, you get an answer. How did she get so smart? Where did that intelligence, knowledge come from? Again, the simple scroll function on your iPad. If you really think about that, you want to scroll. If you want to scroll way down in a document, you swipe fast. And it scrolls as if it's an object with inertia. It starts out fast, it gradually slows down, and it stops somewhere. And if you want fine adjustment, you adjust it slow. Now, so simple, a 1.5-year-old can do it. But it's so, again, the genius is in its immediate connection to normal day hand-eye coordination. Even a 1.5-year-old knows that if I want to push a ball across the floor and I want to push it far away, I push it fast. If I want to push it a little bit, I push it soft. That same hand-eye coordination, you want to go far, you swipe fast. You want to go a little bit, you swipe slow. It is so natural, so intrinsically obvious that people pick it up without even thinking. It's brilliant, but incredibly complicated to accomplish. As John talked about earlier, the human genome, how did it get sequenced? And this next one is he brought out so well earlier, how do you accomplish gene splicing, and this idea of how do you even see it, something that small well enough to manipulate it. And the idea that it couldn't be done without all these multi-disciplined people coming together, without scanning electron microscopes. You could know a gene existed, you could describe the characteristics of a gene, but to see it, to cut it into pieces, to transfer elements of a gene string, and just pick out the piece you want to modify genetic characteristics. Just something as simple as who was the engineer and the scientists and the mathematicians that gave somebody like John the tools that amplified his ability to do his job and his research and pursue the knowledge that him and his team were pursuing. The idea of artificial intelligence, machine intelligence, what is it and what are the implications? I mean, artificial intelligence, machine intelligence, it is a product of human intelligence. So we can marvel at smart machines. Well, that machine, this artificial intelligence is so amazing that machines can do this. And yet we don't marvel in equal degree at the human mind that was the creator of that artificial intelligence. They admire the created more than they admire the creator. The cloud, what is the cloud? You know, I found out my wife was having a conversation with all her friends about, in hushed tones, what's the cloud? They say we can store our stuff in the cloud. What is it? Where is it? And she finally asked me, and kind of like afraid to know what the mysterious cloud was. And when I told her, she said, "Oh, that makes sense. That's really pretty simple." But the idea of the mysterious cloud. How does a 100-story building stand without falling over? Not just, you look at them, they look like giant pencils standing on their end if you look at them from a distance. You wonder, how does that thing not topple over? And even more, you look at the weight of a 100-story building sitting on that foundation. Can you even begin to imagine the stress and strain and, how do you design something that can support all that weight? It goes up 100 stories. It probably goes down about 3 below ground for the foundation. How does that thing stay up? How does a product you buy at Walmart get from China to here? You got logistics and shipping and the cranes you saw in the video that take them off the big container ships, put them in a yard, eventually transfer them to the trucks with all these automated, gigantic stacking cranes, which are fully automated, the giant robots with all the characteristics of intelligence, touch and feel and vision, and I'll show you a little bit about what a machine eye looks like and how it's perceived in the computer world. When you send a document to a friend, anywhere in the world, you get on and you send a photograph or a document to a friend anywhere in the world, and it gets there. 5 megabyte file, it gets there, and all 5 megabytes, all 8 times 5 megabytes worth of bits, little ones and zeros, they all get there and are put together in the exact same sequence, not a single one out of place. And it goes over wired connections, it goes over air connections, it goes over satellite connections, and it gets there without a bit out of place. How is that possible? The idea of you got 20 kids, 20 young people sitting in a room, they're all texting on their phone. Ask them, wait a minute, you're all texting on your phone, and none of these phones are getting confused. You're all having independent conversations. What you send on your phone only goes to one person. It's the only phone in the world that's picked, well, except the NSA, we'll ignore that. But ideally, it just goes to the one person you want it to go to, and they send back, and you're in your room with 20 people, and your phone is the only one that's going to bother to listen to it. 20 other phones in a room, countless millions in the world, all kind of electronic noise, TV frequencies, radio frequencies, cell phone frequencies, and all these digital signals flying around, radio waves. And this phone, your phone is only, hundreds of billions or trillions or gigabytes worth of bits worth of information flying through the air. And that individual phone says, I don't care about any of that except the how many 0.01%? That's what I care about. I'm going to listen to just that and ignore the rest. So the idea that you can have 20 people in a room having a conversation, we can't hear each other speak because of all the background noise conversations. That phone's not getting confused. How many 250-page books can you fit on a 32 meg flash drive? About 2,560, and that's not even, that's a medium-sized flash drive nowadays. 2,560 books are based on statistics I read today, and it's about 215 years worth for the average reader that reads about a book a month. You saw a photo of, in the video clip of one of these big container cranes that transports the containers all over the world. The biggest ones are over 1,300 feet long, 200 some feet longer than a Nimitz class aircraft carrier. They carry up to 19,000 containers. It only takes 13 people to crew one of those. imagine how much automation and technology is involved in a boat that, transits the oceans all over the world, gets to where they're going. It only takes 13 people to crew that boat. Now, how many transistors on an average IC chip? Well, the latest main integrated circuit chip on the latest cell phone, 2 billion transistors on a silicon wafer, 1 square centimeter. Now, as an electronic engineer, I can understand the digital circuitry. I cannot even begin to fathom how you etch that many transistors into a silicon wafer, 1 square centimeter. And as John pointed out, that's where the multidiscipline comes into it. Somebody's got to figure that out. Somebody's got to know how to do that, or all these other things. If somebody didn't figure that out, the engineers that write the software and the people that use the software to solve problems couldn't have gotten a start. Some simple facts. STEM professionals, we do the incredibly complex, and we accomplish the incredibly complex, and we disguise it with user interfaces that are tremendously intuitive, and as I said earlier, in some cases even a 1.5-year-old can do it. Why is it so hard to convince the world of what a great career STEM professionals have? Well, the problem is, none of us are going to pass as the most interesting man or woman in the world. We're not the people in the Dos Equis beer commercial saying, I use applied mathematics when I'm selecting a beer, and it always gives me the best choice. Yes, developing the necessary skills takes work, but you don't have to learn it all, and you don't have to know it all. You learn the basics, you get the basic tools, and a STEM profession, you will learn as you go. Learning's built into the job. John learns every day, I learn every day. By dealing with people in other disciplines, it gives us access to knowledge that we cannot possibly have ourselves. You rely on the team. It is, as John so clearly pointed out, it is a collaborative world. Nobody, the superstar STEM professional, is a very rare breed. Even the one that wins the Nobel Prize had a team of people behind him giving the tools and the background knowledge that he needed. Okay, that person made a breakthrough. He could not have done it without a team of people with a lot of supporting knowledge and tools. And you're going to have multiple careers in STEM because technology is changing so fast. I've been at it for 30-some years, and I probably had 3 different careers, not because I changed companies, not because I changed professions, but the technology changed, the tool changed, and the things I had to work with changed. I talked about the collaborative stuff. Knowledge grows exponentially. By some estimates, knowledge, at least technical knowledge, not so much in the core sciences, but in the technology world, they're estimating now that knowledge doubles every 12 days. That's an incredible statistic. So as a STEM professional, you have the privilege of standing on the foundation of knowledge built by everyone who's worked in related fields or supporting fields. The opportunity to use that knowledge to the benefit of individuals in society, and an inherent responsibility to add a nugget or two to that knowledge base as you go along by sharing with your colleagues, your peers, and writing it down and documenting it in a way that is available to others. Just a quick graphic of how technology progressed. We started out with the transistors in the 50s. That is a key device that makes the digital world possible. But you couldn't make a supercomputer out of those. Too many of them, too much power, wasn't practical. That led to the integrated circuit. The integrated circuit led to the microprocessor that led to personal computers and all these smart electronic devices that are such a big part of our day-to-day lives. With the advent of the PC and all the stuff that came with it, opened the door not just for what computers were supposed to do, which was complex mathematical calculations, but it opened it up for software, word processing software, communication software, animation software for movies. The existence of that device opened up fields that were unheard of. The idea of making an animated motion picture was not possible until when that became available. Creative minds learned how to use that as a tool to broaden into fields that were unheard of before that device became available. This quick picture, these are one of the containers you saw in the video, one of the in the shipping containers. What you see on the left is a digital picture of what a laser eye sees. And that little circle there kind of, captures to some extent, this is the raw data, pretty much the raw data, what you get back from that laser. That kind of shows you where the container is. And basically what you've got is raw data. It takes a tremendous amount of statistical analysis and applied mathematics to turn that into something a computer can actually use in a control algorithm. So these big automatic cranes I showed you, and this is somewhat refined. It starts to look a little more real. You can almost see the edges of the container, the sides, and the truck chassis underneath it. So this is after it's gone through some algorithms to define that data into something the computer software engineer can look at that and get real world coordinates and try and take a big machine with a big hand that's dropping that container down. And that big robot has bones, it's got the steel structure, it's got tendons and cables, it's got muscles and motors, it's got a digital eye, it's got sensors in the tongs that pick up the container, and it can pick up several tons and literally drop it down with a 5 millimeter precision, with about as gentle as somebody laying a newborn baby down in a crib. And without STEM professionals, I mean, when people say they don't think science and technology and math and engineering are relevant to them, the challenge to that is, okay, maybe you think it's not, but are the devices, all the things that make your life so good, are they relevant to you? You're probably going to get in and say, oh yeah, I can't live without my smartphone, I can't live. Well, without STEM professionals, those devices don't exist. Okay, thank you for all you do and teach well. As John said earlier, it depends on it. And what I'd like to show you now, and you're welcome to come up and play with this. I think I'll go over my time, I hope. This is a 3D, that little gizmo on the table, that innocuous little gizmo, is a 360-degree scanning laser. Okay, this is what this is semi-processed data. What you get from the laser scanner is a bunch of what we call a point cloud. And even each one of these little dots is a laser sending out a signal, bringing it back and saying, okay, the distance between my focal point and that object is whatever. And so basically it's constantly scanning, sending out these laser impulses, measuring data, and it's feeding back raw data to an algorithm in here. Now that algorithm semi-processes it to give you a 3D rendering. If you were to get the raw data, it would just be a point number, a point identifier, and a distance, and some trigonometric data about angle from some reference coordinate. But as you see, you can get up and walk around and you can scan in, scan out. You can get right in the middle of it if you want. You can kind of change the angle. You can look, from the top, the bottom. So there's everybody in the room. You can kind of see the tables and the people. And again, this is what. That's a machine eye. Okay, so it takes somebody to figure out how to take those laser impulses, come up with something that says, I sent it, and light travels 186,000 miles a second. This thing's going 5 feet. So it somehow is measuring a time interval of how many nanoseconds, and it's translating that into a distance. Now, you have somebody that's got to figure that out, that sensor technology. That gets networked over the optical nerve, the Ethernet signal, to the computer, where the brain starts processing it. So this, these big beefy crane robots we talk about, it's like they are a good example of state-of-the-art machine intelligence. Again, it's got, eyes, and it's got sight and touch and locomotive ability. Can't smell, you can't hear, but it's got at least two of the major senses present and a brain to process them. Okay, questions?